I have only
Okay, you're on
intent.
mute.
Hi, everyone. There's no one here. It's okay.
I'm
Right.
battling a cold, so I don't know how long I'm
Oh.
going to last. I got a baby pulse.
Yes, and don't worry about my talk. It's all about GMT, so it's more fantasy than actual science.
So, Lars, can you join the Hangout to see if it's working?
Sure. Now, how would I join?
He has. You both have invitations in your email.
Oh, okay.
Just Jan wanted to see it, and we didn't want to do it in any obtrusive way. So the easiest way to do it is just broadcast the whole thing on Google Hangouts. See if that works. Yes. Great. So it's working, and
You know, I didn't
Passes
mind
going under 6, passes going over 6.
more crossbars.
what? You should turn off your microphone.
Now there's a huge delay here because now you just asked me if I could check it.
That's fine, but just turn off your microphone.
I'm turning mine off because I have my Wi-Fi off and I don't get email while speaking.
If the whole thing is delayed, see, they can't talk back. That's the whole idea. Sorry, guys. So here's what.
Does that go against mechanics?
Here's the whole paper for people who want the whole paper.
Includes me.
There's only 5 copies, so you have to really want the whole paper. I have the figures separately.
Actually, you can share it.
There's 15
I need the
copies of
title of the
the
paper
figures.
once I'm back on Wi-Fi.
Wait a minute, where's the other side?
Email from Jan, it works.
Yeah, we know. Thank you, Jan. Okay, so here's all the figures, for which there's 15 copies, so that's sort of okay. And there's 15 copies of that.
Thank you. The pyramid scheme.
And then there's 15 copies of that.
Whiteboard. Two whiteboards.
It's two-sided, yeah. Hi, Jan. We're sorry we made it so you can't talk back to us.
No, we're not.
Scott says, no, we're not. Hey, Charlie, do you know where Chris Vasey is? We need Chris for this conversation.
Okay, I suggest we get started. So for those of you who are not aware, we actually have someone joining us from Vienna. Jan Frohlich is sitting at the other end of Alyssa's laptop following the journal club discussion. We're trying to experiment and see how that works. It's set up in a way so he cannot talk back to us.
He can text in the
He can
Hangout.
text. He hasn't, as far as I can see, he hasn't made any comments, and he hasn't properly checked in yet. But
No, somebody
No,
said he's
he
here.
sent me an email saying
yeah.
I was not properly checked in. He said.
Anyway, so we're going to start off with Alyssa and a paper on subtly Kennicutt-Schmidt relations.
So Charlie just reminded me that I missed his talk, and then I meant to hear what he said. So there's 15 copies. We can turn the lights on. It's kind of dark in here. Does somebody know how to turn the lights on?
Yes, that is probably also set up in the
Since they changed it, I don't really.
Yeah, I think it needs to again.
I'm just afraid to touch it once it works.
That's better. The projector is mostly for reference, but the pages, I don't know. I kind of like Journal Club with the actual paper and actual pages. So anyway, what I was saying is that Charlie gave a talk that unfortunately was conflicting with our faculty meeting, and I couldn't go to his talk, and then I wanted to know what he said, and so I'm very glad he's here, and he reminded me that I promised to come hear what he said, and I haven't had time to do that. So when I'm totally embarrassed and I don't know what Charlie said, Charlie's going to interrupt me. Okay, so there's this paper that's by Rahul Shetty Paul Clark and Ralph Plesson, who are friends of ours in Heidelberg. And Rahul has become a big fan of hierarchical Bayesian fitting. And this paper is actually a follow-up to much more complicated work that he did with Brandon Kelly, looking at all of this kind of Beguil et al. Data and other data from Adam Leroy and other people for individual galaxies and looking at Kennicutt-Schmidt relations. And so I'm going to assume that everybody here vaguely knows what a Kennicutt-Schmidt relation is, but I'll get to that in a second. Okay, but it's basically these relationships between how much star formation there is and how much stuff there is to form stars out of. And the problem is that different people mean different things by that relation, which is what this thing on the screen is about. So everybody should have a copy. Oh, I forgot. This one we'll get to later. There aren't as many copies of this one, so like try to give this one to every 2 people. Okay. Okay. So anyway, so this paper. So in this Bayesian fitting world and in a lot of other work that people have done, people have found what's called a sublinear relationship between the star formation rate and the amount of stuff. Okay. So let's just, in the simplest possible case, right, that you had a molecular cloud of some kind that was a precursor of stars, right, and every molecular cloud turned into stars with some constant efficiency, then if you made a relationship between the star formation rate, the surface density of the star formation rate, doesn't even matter, okay, but total or this density, and the amount of stuff or the surface density of stuff, it would just be linear. There'd be some efficiency constant, and that's it. It's done, okay? But we all know that that's not exactly the case in reality, right? Not every bit of gas in a galaxy turns into stars, and not necessarily the same kinds of gas in different places in a galaxy even turns into stars, right? So there's this whole argument about whether or not the environment in which you have a particular density of gas matters to the star formation rate. Okay, so people have gone, the history of all of this is Schmidt and did this first, and then Kennicutt came along, and what they were talking about is ways to measure the amount of stuff, the surface density of stuff, be that H1, H1 plus H2, CO, dust. Many people have used many different things, and that's a big problem, okay? And then the star formation rate, for, again, which people, as you probably know, use many different things. H-alpha emission from stars, reprocessed radiation from stars as dust emission, which is one I particularly hate because that winds up both on the y-axis telling you the star formation rate and the x-axis telling you how much stuff there is by the amount of dust. So anyway, last summer I was at this meeting in Ringberg, and a couple of other people were there too, about connecting galactic and extragalactic star formation. And I got so fed up with these talks where people were talking about Kennicutt-Schmidt relations, and they were talking about different things every time, and then people were talking about things that related to Kennicutt-Schmidt relations, that I made this chart. And so I'm going to try to put this paper that Rahul wrote in the context of this chart. So let me just explain the chart first. So if you go to the bottom here, okay, and so sigma star means the surface density of star formation or the surface density of the star formation rate. For the purposes of this, it doesn't matter. Okay, it's how much evidence of star formation is there. And then on the x-axis is what is the overall surface density of gas in a galaxy. Okay, and you see here up at the top we have this scheme where you go from a universe that has a certain number of galaxies. Those galaxies have things we call GMCs inside of them. The GMCs have stuff that gets called dense gas, and then the dense gas have things that get called dense cores that are more immediately precursors of stars, but not necessarily even there a one-to-one correspondence, and then you make stars. Okay, so my hypothesis is that the reason that there's so much confusion in the world of Kennicutt-Schmidt relations is because sometimes people are talking about different phases of this process, and not even necessarily one step, but like going all the way from galaxies to stars, okay? So that's what this bottom one is here, okay? So people are saying, okay, if I know the surface density of a galaxy, I can predict its star formation rate. And if you look at the data for Kennicutt-Schmidt relations, this is true with a scatter of a factor of like 100, okay? I'm not exaggerating, okay? But, you know, it's like over many, many orders of magnitude, so it looks pretty good, right? But, you know, arguably we would like to be able to do better than that. Okay, so then the way in which people tried to do better is they said, okay, well, let's look at just molecular gas, because we think we know anyway, that atomic gas doesn't do that much in terms of forming stars. So that's what this next step up here, and you see this arrow that says efficiency. That means that in terms of the amount of gas that's on the x-axis, less and less of it matters as you go up here, where, well, more and more of it matters as you go up here, where you're talking about cores turning into stars, whereas here you're talking about galaxies turning into stars. The efficiency is much less. Okay, so anyway, so if you go up this side of the diagram, you see that you talk about the original sort of classical Kennicutt-Schmidt world, where you count all the gas. Then you can say, okay, I'll only count the molecular gas by counting CO. And this whole paper is about, are you really measuring molecular gas, and is that really the way you should do it in measuring a Kennicutt-Schmidt relationship, by counting CO? Okay. Then there was this famous work by Gao and Solomon quite a while ago now, where instead of using just CO, they decided to look at dense gas tracers for whole galaxies. And that's what this Kennicutt-Schmidt quote-unquote HCN here means. So that means look at a dense gas tracer like HCN, and Shane knows a lot about this, so he can tell us more. And so the slope of the Kennicutt-Schmidt relation gets closer to 1 as you kind of go up in this direction.
But Alyssa, you have to realize that you can't, that in those relations like Gao and Solomon, they did not do surface densities.
This is all true, okay?
And,
so
and it may not be quite the same if you did it in surface density.
This is true, and so over here you'll see the other part of this pyramid has to do with things like that, okay? So I'm just going up the right-hand side for a second, and then I'll get to Charlie's point. And so then, you know, my other sort of bone to pick is that there are then people who go, like there's this Heiderman et al. Paper from the C2D work, which says, you know, what's the star formation efficiency in very dense gas? And they're using sub-millimeter emission from cores, and then they're saying what's the Kennicutt-Schmidt-like relation between that and star formation. And once you get to the thing that is the immediate precursor of a star, okay, the mass spectrum of those and the efficiency of those and the slope of this relationship better all get pretty close to simply 1. Okay, right? Because you're just taking the stuff that's going to turn into a star, finding it, and saying, oh, wow, look at that. That has the same distribution of the stuff that's going to be stars. So to me, the further you go up this thing, the more you get toward a sort of tautology. Okay, so somewhere in the middle, there's a lot of interesting information. Okay, and so over here, what this shows is that you can actually make relations between, you can hop, right, through any of these steps. And people do that not necessarily knowing that they're doing that. Okay, so if you look at, for example, these beautiful column density PDFs that you get from Extinction that try to tell you how much dense gas and how many cores there are in the dense gas and how much dense gas is there in the less dense gas, those give you a relationship between, say, the surface density of dense gas compared to the surface density of full GMC, or the surface density of cores compared to dense gas. And so you can make any one of these relationships if you define thresholds or if you define some structural hierarchy. So I'm not going to go into that whole thing, but that's why this was made, because people were giving talks where they were essentially saying that they were talking about this, where in fact they were talking about some parts of what go into this. And so the idea of this being a pyramid scheme is that in order to actually predict what you should get here, you actually have to understand what causes the physics of all of these relationships that I think just funnel into that relationship. And it may in fact be that there's such a mishmash and randomness that in the end you do just as well by saying, okay, there's some empirical relationship with a factor of 100, and let's just let the cosmologists keep doing that. Okay, so that's the background. Okay, and what Rahul and friends are trying to do is figure out why when you go up in here, using CO, if you try to use CO to isolate dense gas, you actually, even in other galaxies, start seeing a sublinear Kennicutt-Schmidt relation. So let's look at the math for a minute and see what they're talking about. And this is not very complicated math at all, but I color-coded it for you. Just for fun, for those of you who want to relate this page to this page, there's a few copies of this one, and unfortunately I did this color coding before I remembered that I had color coded this, so the color code doesn't match. So that's why there are these like weird ellipses on this copy here. So these colors match what I'm going to show you in these equations. Okay, so let's just go through what they're trying to do. What they're trying to do is, okay, either it could be that this relationship. So let's look at the basic Kennicutt-Schmidt, right? It says here's the surface density of star formation rate, and it's equal to some constant times the surface density of, in this case, because remember they're talking about CO, molecular gas, okay, to some power. And I love that theorists would use a capital N subscript mol to mean a power law index. Like most observers in this room would think that means column density of molecular gas. But no, that is, I'm sorry if Rahul is listening, the power law index, okay, in their Kennicutt-Schmidt relation. So it's this number that gets to be 1 when you would magically find the gas that is all of the gas, or is a constant amount of gas that's going to be involved in producing a constant amount of stars, okay? So anyway, so we don't care for the purposes of this discussion what this alpha is. It's all about what this exponent is. Okay. And so then they go on to define, this is all very standard, the depletion time, which is just the ratio of the surface density of molecular gas to the surface density of star formation rate. And so that just has units of time. You can see that here. Okay, so we'll come back to that in a minute with an example of M51, which is in figure 1. Okay, so then if you say, okay, how does this surface density of molecular gas relate to measurements of CO? That's where it starts getting complicated. Okay, so there's this X factor that just about everybody here knows about, which is a conversion factor from the integrated intensity of CO here to the surface density of molecular gas. And so the problem is that this is measured empirically, okay, and this is the number that it's measured at here, roughly, and there are big arguments about whether the actual observed amount of CO changes because the amount of CO per H2 changes, or something else about the amount of CO emission that you see changes. So opacity, depletion, well, depletion would potentially change XCO if you measured it only in the gas.
Different depletion time compared to the.
Yes, it is correct. This is not a chemical depletion time. This is a depletion time of turning molecular CO gas into stars, not of losing carbon and oxygen, or CO, from the interstellar medium. Yes, thank you, Lars. Extra confusion.
And listen, that equation's not quite right.
Which one?
Number 3.
Number 3. These equations, by the way, are copied from Rahul's paper. So, what do you object to?
The units.
The units? Which units?
On the right-hand side,
Yeah.
those units are not surface density.
He has, this would be in Kelvin kilometers per second.
Right.
And he has Kelvin kilometers per second. So he has this weird, he has per centimeter squared. It's okay. He's actually changed the meaning of XCO to be in terms of a surface density. So yeah, it's okay. Again, the theorists can use the symbols that we use to mean something else for whatever they want to use it for. Okay. So anyway, I did notice that, but that's why I wrote this out with the units. Okay. So I'm going to just say that there are 3 possible explanations that are presented in the paper. And if you look, I highlighted, not in the copy I have, but the abstract and the conclusions, and you'll see that they say what they're trying to do is explain the sublinear Kennicutt-Schmidt relation, so meaning that this exponent is less than 1, which Kennicutt-Schmidt found it to be more than 1, and people want it to be 1 for some magical gas that's going to form stars, but in fact, a lot of the observations and a lot of this fancy Bayesian analysis shows it to be less than 1. Okay, some of the observations are done by Shane, so we should let him chime in. We still believe that a lot of observations are showing this to be less than 1 for
There haven't been that many more observations.
Yeah. They list about 5 papers in here, and their analysis, their reanalysis of the Gill data.
Yeah, well, for the higher density stuff,
Yeah,
it's still very good.
right.
We're talking about the same.
So let's just say that this is, if it's true that these exponents are less than 1, this is a paper about the explanations. So, okay. So it says, let me read you here. Where is this part? Here we go. Okay. Here we consider the consequences of these results in context, blah, 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 blah. If the CO traced gas depletion time is constant, and if CO only traces star-forming giant molecular clouds, then the physical properties of each GMC must vary, such as the volume densities or star formation rates. So these are the sort of two possibilities, which I'm going to show you now, where you sort of monkey with XCO, for example, to make it so that, in fact, you could have a linear dependence on molecular gas, but you wouldn't have a linear dependence on CO. Okay? Or there's this other explanation that they like. Another possibility is that the conversion between CO luminosity, oh no, that's the WCO, XCO thing. This is their favorite. A more straightforward explanation is that CO permeates the hierarchical ISM, including the filaments and lower density regions within which GMCs are embedded. Okay? So what they want to say is that there's a bunch of CO that basically doesn't contribute to star formation at all, and that the different hierarchy of the way that CO is arranged will get you a different CO flux for different amounts of dense gas in different environments. And so I'll get to that in a second. But the rigmarole here is to explain what all these different surface densities are and ultimately how they relate to this pyramid scheme. Okay, so if it's not true that XCO varies, right? So if XCO is a constant, then the surface density of star formation rate is just WCO to the same exponent, to n mol, right? So then if the other choice is that if this exponent is in fact equal to 1 and you have this linear Kennicutt-Schmidt relation and you say XCO is not a constant, then you have that the star formation rate is XCO times WCO, which is obvious from here. Okay? So now, right, you can say if the exponent is not 1, right, then you have to make XCO vary with WCO in order to make the observations work out. And I'll show you an example in a second. And so then he says that he defines this beta so that that's the complement of n mol, right? So that XCO goes then as WCO to the beta. Okay? So if you look at the figures now, so you have these pages that have just the figures. So figure 1, which I think I have here. Okay, so this is figure 1. And he's trying to show you that the suggestion that you have a sublinear slope, this n mol, is borne out by actually the relationship between, this is the depletion time of CO, again, not the chemical depletion time, the star formation depletion time, as a function of the surface density of molecular gas. And this number here, this red line, is a depletion time of 2 megayears, a constant depletion time. And what they're showing here is that the data from Begiel suggests that, in fact, this kind of upward sloping trend is more consistent. And that line converted to units of n mol gives a slope of about 3/4, not 1. Okay? So this is this idea that these quantities shouldn't be constant. And then if you look at what we just said about the relationship between XCO and WCO for the same information, right? So here's n mol of 0.7 corresponds to this line. So you can kind of correct CO, if you will, if you let this conversion factor depend on the integrated intensity. Now that seems to me like kind of a weird conspiracy. And they say in the paper that's kind of a weird conspiracy. We don't like that explanation. But they point out that you could do this if you have a systematic dependence of XCO on WCO. Which, by the way, is kind of weird, right? Because this says that you have to correct the high intensity CO by more, by less than the low intensity CO. In other words, that the conversion factor, so in other words, optical depth would predict kind of the opposite. Okay, so this is very weird. So that's probably wrong. Okay, and they say that's probably wrong. Okay, so we can kind of ignore this here. But they point out that if you did use a constant depletion time of 2 gigayears, like you saw in figure 1, then you can say quantitatively what XCO would have to be, and that's what's shown in the figure that we just looked at. Okay, so then if you say that stars magically form only from dense gas, okay, so it's not that they magically form, it's that the definition of dense is magical. Okay, so the definition of dense is not, Charlie trying to quantify where is the threshold in either volume density or column density that you can get a linear relationship above. It's just some magical gas that would form stars with a linear relationship, so that you could say that the star formation rate was just some efficiency per unit time times the surface density of dense gas. Okay, so then you can get a dense gas depletion time, that's what this is, and then you can say, okay, if I want a dense gas fraction, then that's the surface density of dense gas divided by the total density of molecular gas, which then turns out to be the ratio of this dense gas depletion time to the CO depletion time. Okay, so then, all right, the idea of this fraction of dense gas here is that it's constant over time and space, so that over a whole galaxy, the depletion time for dense gas is a constant in an equilibrium model. Okay, but then the only way that the depletion time for CO is also constant is if this exponent is 1. Okay, otherwise, you have to have, so this fraction of dense gas is constant if the exponent is 1, but it depends on the surface density of molecular gas if the constant is not equal to 1. Okay, so then you finally get to figure 3. Okay, so this is figure 3, and it just shows for an exponent of 1, this fraction of dense gas, I can't see what this says, the fraction of dense gas over the depletion time for dense gas, because this is normalized by the depletion time, is constant and for this value where it's a linear relationship. But then here's what's totally weird. Okay, so you see those downward sloping lines for the sublinear exponents. Okay, if, for example, you use the M51 number where the slope, this exponent is allegedly about 0.7 or 0.75, then the fraction of dense gas goes down by a factor of 2 as the surface density goes up by a factor of 10. So if you look at this, right, so here's 0.75, here's the surface density of molecular gas rising, but the fraction of dense gas divided by the depletion time for dense gas going down. Okay, so that's kind of a weird structure. So then what they say, and I'm getting to the end. Okay.
But just so,
yep.
For me it was a little bit slower. They're defining dense gas in kind of a relative way, right?
They're defining dense gas as the gas that's going to form stars, is what they're doing.
Right. So is that definition change in any way as you move towards denser gas? Or?
Good question, Scott. So here, the final figure that matters is they say that the way that you could explain this is if this is the standard, I'm filling the word theorist, picture of molecular clouds where you have, molecular hydrogen layer that doesn't contain CO, and then you have these blobs of CO inside that we call GMCs. If you say, well, actually you have all this diffuse CO that never contributes to star formation but does contribute to the surface density of CO that you measure, then that's going to change the relationship between this so-called dense gas and CO as a tracer. Okay, so this is clearly true. It's not, however, something that we didn't really know before. Okay, so because what we're talking about is they're talking about this box. Okay, is what they're trying to talk about. They're talking about Kennicutt-Schmidt relationships that are made from CO, and then they're saying, well, how well does the surface density of GMCs actually predict star formation, and how well does CO tell you the surface density of GMCs? And so if HCN, for example, were a tracer of dense gas, then they're saying that this relationship, which Shane tells us has a slope of about point, what?
Well, it depends on the J.
Right.
Density of the molecule.
And it goes down, right? The slope goes down as you go higher in J?
Right.
Right.
Because you're tracing more dense gas.
So how does that, have you seen that recent paper from the Japanese that they use Apex and did a whole multi-level analysis of I think it was HCN or CS.
I know there was a paper where you get out with a quad.
Yeah,
I thought it was one of the students. And yes, there were two things. They had a larger sample of objects with 5J transitions, HCN, HCO plus. The other thing was they used Herschel data to measure the infrared luminosity and the star formation rate in the same aperture they used to measure their HCN observations. So previously people used to use IRS observations to get a total luminosity, but that captured flux from outside the region that you were sensitive to with a single HCN observation. So with Herschel, they have a better spatial resolution and they can do aperture matched measurements. That actually made a pretty big difference.
Yeah, the only thing I remember from the paper when I scanned it was that they found all the, when they plotted total, not surface, but total star formation rate event versus mass to be linear in all the tracers. That's right.
It wasn't linear in all, so it was linear for all but one when they did this aperture correction effect. If they don't do the aperture correction effect, which will be done Herschel obviously, they get about 0.7. But there's one tracer, I forget which one it was, where after they do this aperture correction effect, the slope is like 4 or something.
So it's steeper than.
Yeah. So I think, they still have a pretty small sample size. Maybe they're not doing the after correction effect properly. I think there's the jury's still out. But definitely it's.
So here's what I think, and then we should let Scott go. What I think is what Shane and Charlie are talking about is, like let's say you had some huge aperture here, right? You would get a different answer than if you had an aperture that was just on one of these GMCs, right? And you would get a different answer if the structure looked like this versus the structure looked like this in terms of what CO was tracing. Right? And so I personally think that the answer to this is going to come from, and this is actually what this paper does say, that sort of this side of the pyramid is really necessary, like how much dense gas is there per galaxy. We have big surveys of whole galaxies, and you can kind of really figure out the hierarchical structure as gas goes up in density, all the way from galaxy scales to cores. And we're trying to do that in our galaxy. Tom Rice and Chris Fazy may get involved in this project, but it's trying to quantify that for the Milky Way, which is very hard because there's distance ambiguities, and it's hard for external galaxies because they're far away. But I think, I didn't do this to be mean. I actually did it to sort out what was going on because, I don't do that much of this kind of work, and the people at the meeting, they were mostly extragalactic people, and they're all sort of talking to each other, and I really hope not necessarily that this particular picture gets adopted, but that some terminology that goes with this picture gets universally adopted so that we can kind of fill in these relationships and then figure out how you would predict the bottom from the top. But anyway, so this is a very nice paper, and I recommend you read the whole thing if you want to know more. And I think that in 10 years the answer to this will look very different once we know what's going on the left-hand side.
So this, you going from lower density tracers to high density tracers. You mentioned with CO in those relations, you have a factor of 100 scatter. Does that scatter also reduce when you go to high density?
I defer to Charlie and Shane. I think the answer is yes to some extent, but it's sort of
Well,
depends.
it's not 100, and the scatter's a factor of 10.
It's a factor of 10 either way is what I meant. Not 100 either way. 10 either way. So does it get smaller when you use a higher density? It certainly gets smaller when you only include...
No, it's only a factor of 10 total in CO, and it gets actually, the scatter goes down when you look at galaxies, when you average over whole galaxies. And we found the scatter in the high extinction stuff is a factor of 3 less than in the low extinction stuff.
So, but that's in
And
the
I don't.
extinction.
The HCN maybe have a little less scatter. I can't remember.
Do you know, Shane?
Well, I mean, the higher density tracer you go to, the harder it is to observe, so the smaller your sample size.
Scatter is not well defined. And when I said a factor of 100, I meant in the original kind of Kennicutt-Schmidt world. In the modern observations, it is true that the CO scatter, once you correct for all kinds
How
of
much
things,
is it time
is
average
less.
if you take, say, a GMC in our galaxy, and most luminosity is from those stars already formed, and the dense gas is sitting aside of it. Right? So in fact, the dense gas in trace is not the one that actually made that luminosity observed.
I'll just end because I really want to give Scott a chance by saying that Rahul does simulations, and so do the other people in Heidelberg. And so what I want is for the simulations to get good enough that they can go measure everything in every one of those boxes with simulated observations of the simulations and tell us the answer to questions like that. Because it's very hard to figure out the answer to that observationally because we can't wait 1 billion years and see what happens.
If you take the other end of it, if you take, say, infrared clouds, it has very little luminosity as positive gas. That will be sort of giving you all the end of the scatter.
Yep.
Yeah. You're only out to the easy that time, so it's more